Hey folks, welcome back. This is a really highly requested video. I'm going to go through every single node in the toolkit, in my toolkit, the add-on that you can find linked down in the description. So this is one that I rely on pretty heavily for geometry nodes because, you know, I've basically built a load of tools which help me and I think they're going to help you. So we're going to go through every single node. This is basically a stand-in for documentation. So I know some people prefer videos to PDFs and I've also not finished the PDF. So down at the bottom of this on the timeline, you're going to see all of the chapters and this is like per node, right? So I'm going to go through every single node, tell you what it does, tell you what it's for, tell you how to use it, and that's about it. Let's begin. All right, so when you get the toolkit, it's going to, it just installs like a regular add-on and it will add a category at the bottom of your add menu. This then has its own subcategories for different categories of node. And let's just run through these. So first one up is bevel a curve. First thing we're going to need to do is chuck in a couple of curves to this. This is very similar to how we actually use like a bevel and a taper curve when working normally. So if I just chuck in, for example, a Bezier segment, this can be our path, and we can see that is drawn in there. My profile curve, I may use a circle. Let's set this to something fairly small, 0.1, something like that. And right now nothing's showing because we don't have a taper. So let's also add in a taper curve here. I'm going to use this quadratic Bezier, which just has 3 points. And now you can see what's going on. We're basically controlling the taper, the radius of this curve with another curve. I know that this workflow is very useful for, you know, for people working on multiple curves. So this is there if you need to just have that kind of conventional bevel a curve experience. And this node has a few kind of default settings. We have resolution, so we can control the smoothness on here. We have tilt, so if you had something that was maybe a little bit more angular, you can set the tilt on here. These are all fields as well. Set the radius, choose whether or not you fill caps. These are fields, so if you wanted to do this along the length or by position, then you can do that. Next up, let's delete this one. Curves, curve attributes. So this one is really just for modifying curves. I can take a regular curve and I can just set the resolution, radius, and tilt all on one node. This just saves you adding multiple nodes to do the same things. And you can even turn on slide click if you want that. So if you're doing lots of stuff with a curve, rather than adding loads of different nodes, this one has you the curve attributes node. Next one, pipes. This one basically just takes every edge or curve and turns it into a skinned pipe, kind of like the wireframe modifier or the pipes node if you're used to Spirograph. So this can work on both a single spline, like a Bezier segment, or it can also work on a mesh. So I can put this on something like a UV sphere instead, and you can see it's going to do the same thing. It's just going to take all of those different edges and, well, turn them to curves, and then curve to mesh, so that you get the thickness. These are not fields, this is just a constant value for the radius and the resolution. Keeps it nice and simple, nice and lightweight. And again, we have that fill caps option just in case you want to fill those caps. So that is the ETK pipes node. Next one on our list is going to be points to Bezier. So rather than using a Bezier segment, we might have a series of points. For example, if you distribute points on faces, and you might want to turn this into a curve. This is a bit of a weird one because it creates this kind of scrawly curve, but in some cases, this is actually quite useful. So I've used this quite a lot for kind of generating fake ironwork, things like that. So I used it in my flower shop scene, and you can always use it with the pipes node as well. So you've got these two basically just generating your stuff on here. And you can see changing the seed on your distribute points is going to change that. I can even do it with the original geometry here. So it's just going through the original points of our actual plane, which you can see there. And it's just turning it to a Bezier, hence the interpolation. So that is the points to Bezier. You can control the resolution. That's about it. Next up, we have got the wire flood. This one is one of these weird high-level nodes that is just a lot of fun. Maybe rather than this, we can just drop this onto a cylinder or something like that so we can have a look at the normals. And let's join these together. So wire flood essentially generates kind of a bunch of wires. We have a density and this allows us to do, as it says on the tin, set the density of our wires. We have a seed, so this is going to allow us to change any random values in here. Now we have a distance as well. This basically sets the maximum distance that a cable or a wire can connect from point to point. So if we have it by default set to 0.5 in all, then that basically means the maximum distance. It can be anything less than, but the maximum distance will be positive 0.5 or negative 0.5 in each axis. We can set this higher or lower. So for example, I might go only 0.1 in X and Y, so we can see we have quite small differences. But maybe I go for 2 in the Z, and then now you can see that we're jumping long distances in the Z axis. This one's always really fun to work with, gives you a lot of control, just throws wires while it floods wires. We can set wire height, so this is essentially the offshoot from the surface, the amount of wiggle. If you want to have like a really twisted wire, for example, you've made a server rack or something like that, and you want to show just the cable nightmare. The influence from gravity, and setting the wire radius. We also have a control just to be able to set the material directly on here, so this will be the material specifically for the cables themselves. That is all of our curve nodes. Let's jump into the fall-off stuff. Fall-off is an interesting one because these don't really do anything useful on their own, but we can use them, for example, for animation or for displacement, stuff like that. And these always expect a 0 to 1 input. In fact, you can see this here. So our input is always going to say 0 to 1 here. So let's think about a way to actually demonstrate these. If I just add a line and we can have a look at the actual shape of them, you can use them for anything, like I said, animation, stuff like that. And I'll show you how to use them for animation in a moment as well. But let's start off with a line. So I'm just going to grab a mesh line. I'm going to make it go in the x-axis, make this nice and small with high resolution. So we're going to go 0.02 and we're going to get 50 of them. And now I can just use the set position. And we're just going to take the X position here, which we can see is actually a 0 to 1 range already because of how we set this up. So let's grab our input position, a vector, separate X, Y, Z. We're going to take our X here. This goes into our 0 to 1. And then we're just going to use combine X, Y, Z and use this as an offset in the Z axis, which is where we're looking. And I'll plug this into the offset. There we go. So now you can see that we have this shape and all of the easing nodes. They're different shapes and I'll go through those, but they each have basically the same controls. We have an ease in and ease out. So if you just want it to ease out, it's going to do that. If you just want it to ease in, the opposite, and you can have it do both. You can imagine why this would be quite good for doing animations, because if you have something which is moving, for example, a cube, and we're going to transform it, maybe in the x-axis by a certain distance. Let's do this over a certain time as well. So I'm going to use a map range. And I'm going to do this twice. So I'm going to take my map range. I'm going to use hash frame as my input. And we're going to go from frame 1 to 50. Let me also set the output range on my animation here, go up to 60. So we're going from 1 to 50 for our frames. And this is going to be mapped to 0 to 1. So now we can use this with an easing node, like so. And then on my output, I can take a 0 to 1, which is what this will output. I'm going to unclamp it, because actually easing back goes outside that range, important to note. And I'm going to set these as positions. So we're going to go from 0 to 5 in our X position here. So now if I shoot this over, we can see that that's moving and it moves a little bit past each time. We can change the constant to make it more extreme. Or we could even set this to be a little bit faster. Something like that. Now we have a few different easing types. So we have easing back, which is the one that we just had a look at. Let's delete that one for now. Let's go back to our line so that we can look at these. So easing back here. We also have fall off easing bounce. Take our X and go into our Z. Here we go. So you can see this one has a few bounces at each end, and again, ease in or ease out. This one doesn't have a constant for the control, but you can see if we view this, we just have a little bit of bounce on there. And it's just going to hit that end. There we go. Nice and simple. We should be getting something like this by default in Blender anyway, sort of fall off nodes. But just for now, we have them in the toolkit. Let's go down again. So we have circular. I won't show all of these animated. I'll just show them on the line from here on. Circular is just a quarter circle, in or out, or both, and you can see that that jumps these together like so. So that's circular. We also have elastic. This one is kind of similar to the bounce, but it goes up and down. So this one can be nice just to give a little bit of kind of cartoon easing. We can get the exponential ones as well. Just a nice little exponential graph. And again, ease in, ease out. All the same controls for all of these. So sine is quite a simple one. It's literally just a sine wave. And again, ease in, ease out. And the last one that we have as a single is easing plus. So again, take this like this, and we have an exponent on this one. So this is essentially our quadratic, cubic, quintic. I'm not sure what the 5 one is, but yeah, basically, let's you set this up however you need. And again, ease in, ease out, all the same. Right, easing mixer. How do we use this one? Well, this one basically takes our original 0 to 1, and it's going to take a couple of the mixing nodes. So let's use easing plus for our ease in, and we need this plugged into both ease in and ease out. We want it to be, you know, both start and stop. And let's just grab a different one. Let's go for maybe circle. So I'll plug this one in again, ease in, ease out, both plugged in. So now we can see with a little bit of control here as well, that we can have 2 different kinds of easing. You can have a different start and stop easing. So that's what the easing mixing is for. You have a little bit of blend in the middle so you don't get any pinches. There we go, nice and easy. Fields, get field item is going to be our first here. Let's grab a cube, and what I'm going to do is this will output a field item. I've got this set to vector, but this is going to basically work the same whether or not you're using floats or integers. It's just going to store them within a vector, but we can continue processing those afterwards as whatever data they were. If I take the mesh coming through here, and the field that I'm interested in, just for demonstration's sake here, will be our position. But again, this can be anything. So this is just going to allow me to show you what's going on. Let me take a mesh line so I can just generate a single vertex. Set this count to 1. I'll use this as the start location. You can kind of see what's going on. We're basically picking an index for the position. This will output that one vector, and then we can just demonstrate this by instancing let's use just a smaller cube here. Keep it all nice and easy with the nodes, and I'll just join these together. All right, so we can see we have this cube bound on the bottom corner. If I turn this up, you can see what's going on. We're basically setting an index. We're picking an index and outputting the field at that index. In this case, it's the position, so we're taking the vector of the point. All that does is just picking a specific field at a specific index. Next one we have is field length. So we can take our geometry. Let me just delete all of these. If we want to inspect a socket, we're going to need to plug this node through to something. So just for this, let's go ahead and just stick this onto an attribute capture. And we can see that the length of this is 8 as an integer. We have 8 points, so that makes sense. If I increase the number on here, it's going to increase the value. Then we have 12. So this is just like your list length node in Spirograph. Next up, we have got map range. We have both float and vector as separate nodes. These may become combined in the future, essentially. We're going to take in our geometry. We're going to be bringing something in. For example, I can bring in the index here, and we're just going to set a minimum and maximum output. So this is going to be correct map range. So it's basically going to be using the list limits from whatever field comes in at the beginning. If I wanted to view this in the spreadsheet, we would just need to plug it in and give it a name. So now we can see that we have all of these values from 0 to 1. If I change this, then we get 0 to 2. So we get this. So basically we have taken a regular map range, and whatever range the field has on the geometry, that is our from, and we can just set the output. Same works for the vector version, except obviously this uses vectors instead. The next one is field Normalise, which essentially does the same thing once again, but no controls, and it will just set it from a 0 to 1. So whatever the input range, it will go to 0 to 1. Let's take our next one, which is field offset. This essentially allows you to take a field and offset the index, so you can kind of shunt it. Basically just does a data offset on your field. It's quite convenient. Next one up, we have got field replace. So basically we can take 2 different fields and replace certain indices with the new field, and it will just output a combined field where you've replaced all of those indices. So nice and easy one to use. Just plug in two fields. This might be, for example, position and a different position. Maybe one is displaced and one is not. Your indices, these plug in here, and that just sets where it gets changed over. Next one, field shuffle. This one's a bit tricky because you do actually lose data. My way works kind of good enough for some stuff, but you do get overlap, so this is the problem. We can see we have just a cube here, and if I was to set position, and I'm going to use this as my new position, so I need to plug in my position, here we go. You can see that we've lost some of our vertices, so it's not just that it's gone into a random order, but we have actually lost some data, and we can see that this is just because we have things overlapping. Now, if you're just doing distributed points, this node is actually pretty good at doing that. So I have used this quite a few times. You do sometimes get lucky whether you keeping all of the points, but certainly until we get a proper shuffle algorithm, this one will lose data, and it does say on here, expect data loss. But to use it, just plug in your geometry, plug in your field, and set a seed. It's just going to randomly shuffle it. All right, next one up, index to factor. This one's just going to take your geometry and pass out a 0 to 1 normalized range for the index. So for example, if you have a cube and you want to pass out something that you can use with an easing node, if you want that 0 to 1 control, or maybe you're going to use this with something like a mix RGB, then this is your friend. This is the way you're going to do that. Index to factor basically just sets your entire maximum index range to a 0 to 1 range. All right, we're into the next group. These are the generators. Always fun. If you've been watching my November streams, you will know this one certainly, or these three, the brick walls. So essentially creates a brick wall. This is the brick arc, and we have a couple of options here. We can pass out the geometry, which will generate some bricks like this, or if you have made your own bricks, let's make a new collection in here. I'm going to add some bricks. Let's just make these a little bit smaller. I don't need to worry too much about the size, because if I use a collection of bricks, it will actually measure them. So I've got 2 cubes. I can set this, that was collection 5. Now we can see that all of our bricks are this one. I just need to rotate these, and there we go. Now we're building a wall out of our new bricks. If I made these a little bit smaller, then you can see this is working. So by default, this node is going to be preferencing the height of the wall, and for the brick arc at least, the angle. So radius and angle, that's going to set the length essentially. If I make this up to 2 meters, then we can see we have a 2 meter radius, we have more bricks. If I set a higher angle, we're going to get more until we go all the way around to a tower. If we have a different height, you've got a different height. So there we go, lots of control in here just for creating essentially brick walls. Because it's an arc, we also have a rotation control, just in case this was set to, for example, 60. You may want to, spin it one way or other to match whichever place you're working on. And also, if you're aligning this to other brick walls, we have an offset switch at the bottom, which just switches which way the offset is working. Now, if you have a specific number of bricks you need, you can override all of the previous data with an X and or a Z count. So now I can say specifically I want 10 high and 10 long. And regardless of how you have this set up, this will output a radius. So without the X count, we can use the radius setting, in which case this will just pass out the radius. With the X count, obviously if we have more of these, we're still using the same angle. So you can see that, but the actual radius will be changing depending on how many bricks we have. So this radius output can come in very useful there. Let's have a look at some of these outputs a little bit more. So rather than geometry, you may want to actually do something more complex, in which case we can pass out the points directly. This just looks like a line because that's how I've made it. And then you can go and use something like instance on points with your input collection. So I can just do this, separate, reset children, pick instance, and there we go. Right, but what's the issue? Nothing's following our curve. So let's plug in our rotation. That's made that all work. And right now this is not giving us like a good result for our width and height. So let's also just make sure that we have this set a little bit bigger. Let's change this off, those 2 counts, and I'll just eyeball this now. We can do it more accurately, but just just for demonstration's sake. There we go. So that's fixed all of our spacing issues. Let's have a look at some of our outputs. So on all of the generator nodes, you're going to find that there is a size output, and this is just the maximum number of points, the total number of points. In fact, if I plug this onto a capture attribute, just so it computes, we can see that we have 276 bricks. Next we have the radius, so we've already talked about that a little bit. In this case we have a radius of 2.62, and that is the radius. We then have XFAC and ZFAC. So what are these? Well, these ones are basically a 0 to 1 gradient based on either the X, which in this arc wall is going to be our direction around here, so it's going to go 0 to 1, and the ZFAC is going to go vertically upwards, 0 to 1. What can these be used for? Well, let's just try plugging them into the scale and we can have a look straight away. So there we go, it's going the other way, but 0 to 1, or the ZFAC 0 to 1. So you can imagine using this for motion graphics, maybe doing some kind of interesting rotations along the surface, different scale of brick, different rotation of brick. I've certainly seen things like this done where we have something like a rotate Euler. We're going to go local rotation like this, so we can twist it in the Z-axis, and then we have a FAC, right? So we can plug this straight through a float curve. That's why the normalized values are always so useful. Let's go for an X factor into our value, into the angle here. By default we want 0, right? That's our base position. And then maybe I come up in the middle and you see we get this kind of rotation going on. So you have a lot of control here, a lot of procedural control for basically mixing and matching how you build your walls. This is just the arc, but we also have the brick straight, which I've used extensively on stream. And again, this works with your custom bricks as well as by default making its own bricks. You can set the brick size and things here as well if you want custom brick size. And again, output the line if you just want those points. It's going to output the size, no radius this time because it's a straight line, but it will give you your X factor and your Z factor, both just the same as before. And again, offset switch on here, just to give you that control. This one, again, is going to preference the wall length and wall height, but you can override that with the X count and the Z count, like so, nice and straightforwards. Next one in here, let's have a look at the brick spline. This one's very slightly different because it actually wants a spline. And let me show you a little fun trick with this. We're going to first of all pick our bricks. So let's grab these, collection number 5. And I'm also just going to come in here, pin the node tree. I'm going to come in and make a Bezier spline. And we can just select this curve now. I do have the issue that it's in the collection, so let's move it out of the collection. And now you can see we have bricks on a spline. Why is this useful? Well, because it means I can come in, grab my spline, make it a little bit longer, make it curved. If you want custom curved walls, then you can do something like that. Now, another thing which is extra fun is if you go into your tool shelf, come down on the left-hand side, you can find a Draw Freehand Spline tool. If I go into Z here, now this one, I do really need to bug fix this one. If you have an even number of splines, for some reason the spacing gets mixed up. So I do need to just do a little bit of a bug fix at some point. But as long as you just make a third one, you're fine. You get that offset back. But you can see what's going on here. I can do something fun like writing things. Hello. And there we go. We get this curve. Now the corners are not pretty. There's not really a lot I can do about that. It's just the nature of very tight corners with regular sized bricks. But you can see how this would be useful. It will align to the lowest point. These bricks are always going to be straight. So just something to be aware of. If I do this, you can see everything moves down to the lowest point. This is actually quite useful if, for example, you have a building on a hill. Chances are you're going to be laying your bricks horizontally. So it's going to basically align it to the bottom, and you're just going to need to change your wall height until it comes up through the floor everywhere that you need it. And again, we can pass out our points instead and do a custom instance with the curve factor, which is going to be along the curves. Let's show this really quickly. Let's grab a instance on points, a input collection info with collection 5, separate, reset, pick instances, and we want to plug in our rotation. So there we go, we're all set. I do just need to make another wall just to make sure we get the offset back. So if I look at the curve fact into my scale, you can basically see that each one of these curves gets a 0 to 1 along its length. So you can do a lot of fun stuff with that. And again, the Z factor, just the same, 0 to 1 vertically. Awesome. Hopefully this is starting to get your creative juices flowing. Let's move on to the next one here, generators. Circle. This one generates a circle. Not really much more to it. So we have a circle here, and we can choose the number of vertices. We can choose the radius. So I can set the radius difference here. And this one makes it a little bit different to the default. We have a U min and a U max. And you can see if I bring this out, we're actually reducing the range of that circle. There is another option in here for center vertex. So if you have this turned off, then it's going to be a straight line, just a chord across. And if you have it turned on, it's going to go via the middle. So this might be useful for motion graphics, pie charts, things like that, where you want a specific slice of node. Now, there is a very slight motion when we touch basically exactly the 360-degree range. And this is because of the number of vertices. So I basically made it so that the number of vertices that you pick is the number of vertices that you see. If I turn off center vertex anyway. So without center vertex, we can see we've set this to 5. We have 5. If I increase the U, you see it looks like it jumps to 4. But this is because, you know, when you're moving this around, if I have this over here, I still want to have that like 1, 2, 3, 4, 5, because I've set 5 vertices, right? Now these are vertices on the rim. The center vertex does add 1. And if you look at the size output here, this will actually say at this point 6. So the size output is always going to be correct for the total number of vertices you have generated. Now again, we have the factor, which is going to be basically 0 to 1 along your radius, your edge there. And we also have rotation. So if you're instancing, so if I plug in my rotation, you can see that these then align to that rotation. And there we go, we can set this however we want. There is the option to set spacing. So rather than using the vertex count, we can use a specific number of vertices. I know that these are a little bit smaller. So let's bring these down until it approximately fits. And now you can see that if I change this, it's going to fit that size basically. So we never have too many bricks here. It can be very useful if you are doing things like radial arrays. Cool, good stuff. Now, this is going to get fairly familiar, this kind of format of geometry size factor rotation, because this is how I've tried to make everything, more or less anyway. Let's have a look at our cylinder. So again, we do have the issue with that kind of twitch when we get to 0, which is just because we don't have a weld, I don't want any intersecting vertices, so this is just going to allow you to basically keep control of the count. And if you're animating this and it's going past 0, you're probably not going to see too badly. Like it'll be like a frame at most that you just need to keep an eye on. It's a very small threshold. So again, we have a cylinder. Let me turn on the wireframe just so that you can see the actual topology here. We have a top and bottom face. If you want to turn these off, you actually do need to tab in, look at your cylinder and turn these off. I'm going to just leave these as n-gons for now. We have parallel control. So this is the number of vertical cuts, the parallel cuts. We have the number of edge vertices, as you can see there. We have the top radius and bottom radius as separate controls. So this is actually quite similar to the cone node, the default mesh primitive, although we also have the angle control on it. And we also have a twist, really interesting for making some really interesting flowing shapes. Just basically gives you an angle that the top, so if I set this to 90, the top is 90 degrees offset from the bottom. Now again, I can set this to use spacing. We're going to set this down as something fairly low. Let's have a look at this with set points. And again, let's plug in our rotation into the rotation, but you can see what's going on here. Now the issue is that we're getting our spacing based on the minimum distance. So it looks like it's widely spaced at the bottom, but it's cramped at the top. If I set my bottom and top radius to the same as 1, and then I set my spacing, you can see that that is actually going to be spaced. Now the issue is that it's spacing vertically and horizontally. It's not just doing the horizontal spacing. You can change this if you want to dip into the node and actually have a go at tweaking some of the maths. It's just it's an option that is available for you again. Z factor. I've actually named this one a bit better here, theta factor. So this is our kind of radial angle, 0 to 1. Everywhere you see fac in Blender, it is a 0 to 1 range. All right, that's the cylinder. Let's have a look at the next one. We have got the ellipse, basically the same as a circle. We have number of vertices. We have a radius y and x as separate controls because that's how you do ellipses. And again, we've got our umin, umax, nice and simple there. Let's jump onto the next one here, generator. Working our way down, grid, one of my frequently used ones actually. Let's just grab this as the grid. It is a 3D grid. It just has X, Y, and Z controls, so you have a count here, pretty simple. Set the number in the X, Y, or Z. If you set this down to 1, obviously you have a 2D grid. Now, the sizing is an interesting one. Just keep everything within the same size, so by default, we can basically set the number within a volume, or you can set this to use spacing, in which case it will use this vector as this spacing vector. If I plug this onto my instance on points and I make my sizing fit these bricks, there we go, something like that. So we can use spacing instead. And now if we adjust this, we're going to be setting the number in each row. By default, this will be centered on 0, 0, 0, but you can turn off centering and then it will be on the corner, just in case you want the corner instead. So it depends what you're making. Can come in useful. And of course, randomization, if you're making a 3D bunch of points, it's actually very useful to have randomization. So this simply adds a random value to the position. Nice and easy. If you don't like it, change the seed. Nice and straightforward. Again, we have a size output. This is the total number, which in this case would be pretty high. And then we also have X factor. So our X factor, Y factor goes in the Y direction, and the Z factor goes in the Z direction. Very useful tool if you want to generate thousands of points very quickly, especially random points in a volume. That is the way to do it. Grid hex and grid try. If you've been following my hexagon world tutorial, you might feel a little bit cheated. We can do this in a single node. There we go. That's all it does. So it creates a bunch of hexagons. Can also output just as centers. So if you want to do your own custom instancing, outputs the size, X factor, Y factor, and it will set a rotation. So what's the rotation for? Well, this allows you to randomize the rotation, basically. You can set a random 60-degree offset per tile, and there's a seed to control that. Side length, so we can control the side length of our hexagons here. And again, we can just control the X and the Y count like so. The other one, which is very similar, is going to be grid try. Pretty self-explanatory really. Makes triangles. Again, set the X count, set the Y count, and that's going to do that. You can see visually it's only one row, but we're doing it in terms of the direction of those triangles. Randomized rotation, again, it's going to do 120-degree rotation random per tile, and this rotation output is going to make sure that every alternate row is, one way or other, so that we're facing and things tessellate nicely. So this is the node for this. We can use this. Set the side length of your triangles. Set whether or not you have it centered. That's an option on both of them. And here we go. So a few more options you have here. If I just show you this, these are our centers, right? Obviously the bricks are not a good example, but we'll just work with it. We have our X factor and things like that. So that's all default. But we also have a row alt. You can see that we're actually getting that alternate row being picked. So this is just a Boolean that, if we look at these ones, is going to select rows pointing in one direction or the other. That is what that one does. Let's move on. We have got the next generator in here as the Icosphere. I went through a lot to try and make Icospheres, and I ended up just using the default one. So the maths behind Icospheres, someone did actually successfully make one, so amazing congratulations to that person. But unfortunately, no, I did not use it. We are just working with the default Icosphere, but we've added a few more options in here. So outputs the number of points. We have a U factor and a V factor. These ones are essentially like our curve, like surface domain. So that's going to be our range in this direction. That's going to be our U, and our V is going to be top to bottom. There we go. If I plug these on to our bricks again, just keep using these. Plug in our rotation, and now you can see everything aligns nicely. So that's good. And we have a V factor, bottom to top, and a U factor, radially. There we go. Now, what about some of these other options? Let's go back to our grid. So we have the radius control, of course. We have a subdivision value, so you can set a number of subdivisions. And we have a umin, umax, vmin, vmax control. Essentially, this lets us cull points, and it is just culling points. Literally, what it says on the tin, you can see we're getting that disillusion of the sphere as we come around there by the angle. And we also have it top to bottom, so you can create these kinds of interesting shapes based on the angles within a sphere. So culling angle for the surface. That will be very similar to the UV sphere, which we'll get to in a moment as well. As the Icosphere, we also have the line. Might be an interesting decision to have come up with a custom line node, but it's actually very useful. I use it more often than the default line node. Essentially, same again, geometry output, size, total number of points. The factor is a 0 to 1 length for the points, and the rotation, well, this one's actually quite useful because I can plug this into the rotation. And if I start moving around these points, you can see that we're getting an actual rotation on those bricks rather than it just being a rotation on the points. So that can be quite useful to get things to align nicely. I can set this to spacing. So if I want this to be roughly brick length and have a certain number of bricks, that's going to work like that. Or I can turn off the use spacing and now we just have a total length. Either way, we're using this number of vertices. But it's just whether or not you want to use this length for the spacing length or for the total length. So I bring this out like this, there we go. So that's a nice easy one to use. Let's go on to the next one in here. We have a very similar one, which is also the line segment. I'll just work through these alphabetically though for now. Phyllotaxis, everybody's favorite. This one just generates Phyllotaxis. So it starts off with 500 vertices, an angle offset of 137.5. So you can see that this is basically the amount of offset that we have per point, 137.5. That is the magic number that gives you the lovely distribution of points. We have a radius in here, which controls the outer radius, and we have an expand, which just pushes out from the middle. This isn't in meters or anything like that. It just gives you a bit of kind of eyeball control to push that out, dilate that center. We have a depth control. This is going to allow us to move this up or down. And we can set the exponent on here, just in case you want some extra control for that. Now, if I plug this onto my points, we're also going to reduce the number of vertices. There we go. Now we have the rotation, and this is useful if basically if you're making flowers or plants, this is going to be your base rotation. So each one of your leaves is correctly aligned, or your petals or whatever. Fall off is going to be a 0 to 1 range from the inside to the outside. So just simply that, 0 to 1 inside to outside, and is based on the positions. So these don't change size depending on the expand. It's entirely based on the index. Obviously the size is just going to be the number of vertices in this one. All right, next generator is the Purz node. This one's kind of a joke, but also you can do some really fun stuff with it. Let's have a look at this. I'm going to just jump straight into rendered view. It's a bit of a weird node, but it does allow you to do some really fun stuff. It's also a very big node. Let's jump in here. I'm going to make a couple of materials just so that we have them. I'm going to make kind of a default one here, and then I'm going to make a dark one just for the supports here. So we have two options for materials at the bottom. Let's start with this veneer material, which I'm just going to set as our default. Maybe I actually set this metallic just so that we have something interesting to look at. Something like that, maybe a little bit darker. And then our wire material. So I'm going to use I'm actually going to set this to a bright color so we can see it nicely. All right, it's a bit gloopy. It all sticks together. It merges with itself when it gets within certain proximity. I recommend not turning these up too high. Things will get heavy quickly. This is using volume to mesh to do all of its remeshing. So if I set this up a little bit, we can see we're losing some of the integrity of that volume to mesh, but that's just to be expected. Start resolution. Maybe I make this a little bit higher and you can see that you bring back those veneers. So that's basically the resolution of your volume to mesh. Veneer count, we have 5, and we can see in here basically 1, 2, 3, 4, 5. If I set these up to a higher number, you can see we're gaining more veneers. We can randomize the Z position of these veneers to give us a little bit of interesting variation. And we can also set the displacement amount. So this is going to basically do a noise displacement on the surface of these veneers. Now, if you have too high displacement, you're going to need a higher resolution to make up for the fact that your surface is stretching. Even at 0, you can see what's going on here. We're basically working on planes, making a grid of planes, and then just messing with it, having fun. That's what this node is about. This node is just form finding and exploration, looking at silhouettes and just having a good time. We change the seed, and this changes everything. We have veneer thickness, so this does what it says on the tin, makes the veneers, these horizontal sections, thicker. We have a cull veneer, which is the amount of the Z facing which gets culled, basically. So if I cull a lot, then we're only going to be left with the stuff which is very horizontal, but we end up with some interesting holes, interesting kind of spatial design stuff going in here. The wire density, this node was actually the precursor to the wire flood node. I made this and I was like, wow, actually that looks like a good time. Wire density basically strings stuff together, makes it look structural. And we have wire radius on here as well, which just sets the radius of the wires, and the wire wiggle, which just sets how random the path of these cables is. So you can have fun with that. Now we have some fake bend going on. This is just a vector rotate really, but we have a center bend axis, and we have some high-low limits and angles. So you can see we can start messing with this, get this to split itself open here, and we can control how much of this gets through. If you set your limits very close to one another, you can actually get some very interesting effects. Maybe we go for a more interesting bend radius. So we're definitely getting something coming through here. Maybe we want to break that open just a little bit. Maybe we actually go all the way around. Let's go 360 or just under. And now we should get this sort of sweep coming around. Let's set our resolution up a little bit higher, and we can keep coming up here. Let's go up to 60. Just bear in mind that this will get slower and slower the more mesh it is calculating. 100. I'm starting to have a little bit of trouble processing this, but here we go. You can just see this node. It's not about really generating a thing. It's just about having fun. There will be some more nodes like this added to the toolkit, or maybe expansions for the toolkit in the future, where we are essentially just doing form exploration rather than making a specific low-level tool. I'm just going to turn down my wire density there a little bit. There we go. Lots of fun to be had with this one. ETK Purz in honor of Purz Beats. Amazing artist. We can see how computation time is taking 1.5 seconds to compute this node. All good fun. Right, let's jump on to the next one. Generators. Under Purz, we have our line segment. Back to the normal stuff. Let's have a look at this. Right, we have a start and stop. So these are our in and out points on here. Pretty simple. We can just position our ends. We can choose whether or not we use spacing for our points. So if we use this on our instance on points, right now we have a set number of vertices. But if we change this to spacing, then I will use approximately our brick length, and I can plug in my rotation. If you ever want to switch your rotation like I do now, I'm just going to jump in, change this over to X, and that just makes things a little bit easier. So there we go, something like that. You can see now I'm using the spacing, that wherever I move this to, we're changing the number of bricks or points specifically on the line, and that is controlled by the spacing. It will not go lower than your spacing, but it may be higher. But it will never be higher than 2 times your spacing. So that's just something to be aware of. The longer your line is, the more accurate it will be to your spacing. The difference between 2 and 3 points versus 101 and 102 is going to be much, much smaller if you think of that as a percentage. And again, of course, size and factor are outputs. Right, next one we're going to be adding is going to be the Spirograph. If you have watched my Spirograph video, then you're going to be quite familiar with this one. This is essentially what we made, although I believe we made that one with the attribute system. And this is, of course, using fields. So we have a total number of vertices. We have the draw amount, which you can see is basically a progressive drawing of the line. Now, regardless of what this draw is, you will always have that number of vertices. So if you are instancing on this, you may run into trouble. However, you can just use this with something like the curve pipe node that we talked about earlier. If I increase that a little bit, drop my radius a little bit, now you can see we've actually got a mesh. So that's nice and fun. Awesome. So 2 pi, that's our full rotation. We have the number of turns, which we can see here is 4. And if you go higher, then of course that's just going to increase the number of turns that we have. You can make some very interesting shapes with this. Have a good exploration with it. We can set our minor and major radius. So our major radius is kind of the main shape, and the minor radius is then a circle that we draw along that circle. So that's why we get this kind of interesting shape going on here. Now, if I were to do something like this, and plug in my rotation and then set this to a line rotation, things will follow fairly close to the actual direction of the line. This is kind of a less useful node for explicit construction like this, but just using this allows me to show you the output. So we have the size, of course, this is just the total size. In this case, that would be 59. We have a factor. This is 0 to 1 along the curve. And we have a fall off, which is 0 to 1 from the center to the outside. So this one may be more useful just for kind of general use, but the factor is going to allow you to do some kind of interesting progressive animations along your spirograph. Next up, we have got the torus. There is not a default torus in geometry nodes, so let's grab this. So we've got our, looks like a fairly long node, but it's actually quite straightforward to work with. There's just a few things in here to be aware of. So we have our geometry output as default, we have our size, we have our U factor and our V factor. Let me just show these ones first. If I use my rotation in the rotation, we can see things kind of stick on. It's not the best. It's not the best surface. They don't really follow our actual mesh here, but they do track in quite a pretty way actually. The U factor is radial, you can see like that. And the V factor is actually around the donut. If you've watched my blue rose, the endless bloom video, this is the node that I used, and it was this factor that I used to animate those petals. Let's have a look back on here. So we have our minor radius and our major radius. Of course, this is just our major radius here. Minor radius is that one. The major and minor segments, this is going to be our outer segments here and our again, minor segments in here. We also have a twist, so this is basically going to allow you to twist along the length. Now, depending on your resolution, you're going to want different values. The most kind of foolhardy way of doing this is just to set it to 360 degrees or something like that, so you can be guaranteed that you have a nice connection at the end there. And you can see how this could start making some fun shapes. We also have a U phase and V phase, just jumping down to the bottom here. This is going to basically move, like spin it that way, or the V phase is going to spin it into itself. And again, the V phase is what I animated for my endless bloom. Now the Umin, Umax, Vmin, Vmax, these are our surface domains. You can see what's going on here. I can set my different U and V minimum and maximum domains. So if you want something quite interesting, we can do something like a full U domain. We could then do something like changing the number of twists. You can see that these don't quite play nice, and this is because of our V and U phases. If I set that back to 0, then our 0 stays where it should be. Now, if I set this to something like 1080, then we have 3 rotations. We increase the number of segments here so we get something smooth. And then you can basically see that we can get something really nice here. If I set this minor radius up a little bit higher, do something like that, we have this really lovely ribbon, and then we can just chuck on something like a wire flood, join this up so we can see everything. I need a little bit more distance on my wire flood, so let's set this to 2 so that we can get these strung up. A little bit more control from my gravity, so that these look like they're hanging down, and a little bit more density. Set my wire material to red, and there we go. Easy creation of these like really interesting freeform structures very, very quickly. All right, that's basically covered the torus for you. Let's go on to the next one, generators, UV sphere. You're all familiar with this as a default node, but this essentially works the same as that by default, but it's also got the extra polish. So we have our geometry, size is our total number of points, U factor, V factor. Again, these are going to be our different values along the different directions of our surface. So if I plug in my rotation, we have this. Again, this is not really following a locked rotation. This is free pivoting rotation, which is why we get the kind of interesting polar formation. We see that we have this radial stuff on the U factor and a bottom to top on the V factor. So that's controlling that stuff. And if we have a look back on here, we also have things like our U count, V count, which is going to be our different resolutions, radius, of course. And we also have our U min, U max. So if you want to control this, make a certain shape. I've done this with making displays like this, wraparound displays. Done a few things, and we've also used it for, I think we did it in one of the first live streams when we were making the demon donut. We did a full sphere like this, and we just like had that instant, nice and easy half, just how you want it. So no need to delete stuff. We can have complete control over how much of our sphere we actually have on display. So that's the UV sphere. It's just a regular UV sphere with a bit of extra polish. Final one here doesn't seem like it would be very useful, but occasionally you want it. Basically, it's just a vertex. You set the position with a vector, nice and easy, and it outputs a point. That's all there is to it. Let's carry on. So we have some mapping stuff. So we have the basher. So the basher node, if you've watched my tutorial on getting rid of tiling artifacts, I think we make a node called the untiling node. There's a modified version of that called the basher, which is available on my Gumroad. And that is for texture bashing. Basically, triplanar untiling bashes textures, but it does it in geometry nodes. And it also does it in 2 different variations. So we're going to just show this nice and easy with the sphere. Let's grab just an Icosphere. Let's go for a few more subdivisions. Let's go up to the 7. So when would you ever use this? Well, I'm going to actually just jump ahead and show you another node, which is going to be very useful for this, which is the Displace texture node. It allows you to take your geometry and displace it with a particular texture. You can set the strength mid-level, whether you're going by normal or vector. In this case, we're going to go with normal, which is the default setting. Take that on if you want it to be vector. I'm going to just grab a new image in here. So let's open. If I maybe just grab one of these, let's grab this displacement. Now, if I just plug in this like so, we can see we have a huge amount of displacement. So let's turn down our strength a little bit. And we're going to need some more resolution. Now, working on geometry with no adaptive subdivision does make this an interesting challenge. Let me also just smooth shade like so, just so that we have something to work with here. So you can kind of see what's going on. We have got our texture bashed over the surface. So we're basically putting in all of these places, and we're using the fast one here. Now the output from this node also has blended and scale. And scale basically allows you to go through like a divide node if you want to control your strength by the scale. And that way you can just set your scale over here and it's going to pass it out. We've done this similar kind of thing with our texture tutorials in the past. Let me show you why you would want blended instead. You can see on these edges, well, you can see edges. That's the issue. So the blended version, if I join this one up, this one's going to take a little bit longer now. So we can see we changed that from the texture displace taking 73 milliseconds to it taking 539. That is a pretty significant increase. Now, of course, we're using a lot of polys here, but that's a big change. But the issue is, it takes a lot of nodes and it takes a lot of Voronoi in particular to get this having complete smoothness. Everywhere is blended nicely. So now I've got this set up, and hopefully this will be fairly performant. This is taking around about 4 seconds, 5 seconds to perform. So we have scale. If I set this to something like 0.5, then, well, it's going to scale the texture to a sort of twice the size of it being a 1. Now we have triplanar edges. This is kind of like a wobble. In fact, let's go into fast and we can have a look at this a little bit clearer, because we actually want to see our triplanar edges. So if I set this down to 0, then we will see that we have some edges dividing our mesh up. You can see it really clearly here. These are the triplanar edges. This is where each axis is projected. If I set this up to something like 0.5, you will see that this gets distorted. A lot of wiggle on that. 0.2, 0.1 is the default. That's probably fine. If I go back to a scale of 1, so we get a few more tiles in here. Our cell edges, this is essentially the same. So if I set this to 0, you can see we have these straight Voronoi edges in here. If I set this up to 0.2 as well, suddenly our edges are a lot more difficult to look at. Now the fall off, this is to do with our blended mode. So if I set this back to blended, we get this nice fall off. If I set this to 0, it's going to be pretty close to nothing. If I set this to 1, then it's going to merge stuff in a way which is actually not very helpful. So 0.2, 0.5, something like that is probably going to be the best bet for you. You're not going to lose too much definition on your texture, but you will get rid of those edges nicely. Now, cell randomization and cell rotation. Cell randomization is basically on the Voronoi when you set it from a regular pattern of grid squares to a Voronoi pattern. And the rotation randomization, this is something you may wish to turn off for bricks because bricks have a very specific laying pattern. So there we go. Now, we also have hide seams. I recommend you watch the tutorial for that, but essentially this zooms in to the image and pushes the seams out. So if you have a non-seamless texture, you will want to hide your seams to prevent any additional stuff. So just zoom in a little bit. 0.1 should be fine. Now there's cell randomization and rotation randomization. These can be driven by your seed value. So if I change this, you can see we're going to get different rotation, different cell positions. All good stuff. Right, the basher, that's us done with the basher. It basically allows you to bash textures. We've got a bunch of kind of interesting ones, but let's have a look at, before we get onto the space conversions, let's have a look at some more of these texture, most useful for texturing anyway. So if I grab my window coordinates, let's start at the bottom. This one is one that we're going to be familiar with from shaders. If I grab my camera, bring it to my view, let's go for a default here, 1920 by 1080. We're going to use our camera object as the camera in here. I'm going to use this as the vector. I'm going to just bring in, let's just use an image texture in here. So this is going to be our vector. I'm going to grab that same sculpt and I'm going to put this into the same displacement. So now you can see as I move around, this texture is actually sticking to our camera. This is what window coordinates do. Essentially a 0 to 1, left to right for our camera. If I draw this on, we have U being 0 to 1 and V being 0 to 1, or X and Y. You set up your camera. Unfortunately, I can't sample this implicitly, but we're just going to select our camera, put in your field of view in degrees. That's an important one. If you want this on a driver, then come into your options here, change your millimeters to degrees. You can copy this as a new driver, go back in here, and I can paste that as a driver. So now if I change my camera, even if this is in millimeters, you can see that this will actually correct itself. This will update, and you can see that there. If this is something that you need, it's how you can do it. Let's have a look at the next one, triplanar and triplanar blend. These are kind of a pair. You don't need to use them both. You can just use triplanar. Triplanar is very useful if you have something like an image, which is a two-dimensional texture. So if I just, let's bring back that image once more. If I bring in triplanar here into the texture, you can see that we're now, rather than this just being projected from the z-axis where you get this stretching, triplanar allows you to do box mapping. Now there is also a blend, because if you remember from our basher node, you get seams over your triplanar faces. So what you're going to do is you're just going to grab an image texture. I'm just going to duplicate this one 3 times, one for the X, one for the Y, and one for the Z. And then we can use our triplanar blend, and we simply plug in our X, Y, and Z axes, and then this is our color. If I bring back my Icosphere, I just muted that so it was a bit faster. We can now see that we are getting blending over those corners. If I set this down to 0.1, then it's a little bit closer actually. We want a nice tight blend so that we don't have an edge, but we don't lose the definition of our texture. So 0.1 is probably a good default actually. Set this to 0 and you'll get your edge back. Set it to 1 and you're going to see overlaid textures. Some textures this will be fine, things like tree bark, ground for bricks and stuff like this. Probably best to keep it nice and tight. 0.1 is going to be your best bet. Let's jump on to the next one. We will have a look at looping coordinates. What could these be used for? Well, if you have a noise texture or a Voronoi texture, you might want it to be tileable, and especially if you're making game assets or something like that. So let me just set up something here. We're going to grab a grid, and I'm actually going to instance this on another grid just so that I have a little bit more control. I want to basically prove to you that this is going to be tileable texture. So here we go. I have 3 identical grids like so. I'm going to realize these just to make sure that you know that these are definitely unique geometry. So we're going to increase the number of points that we have. If I show the wireframe, you can see that's nice and dense now. It's got to 100. And we're going to be doing looping coordinates. And let's use this again with a texture displace. And we're going to bring in a texture, which is going to be, let's use a Voronoi just for now. So let's use the distance. This is our texture. We can see this is here. And right now, these are all different, right? Right now we can see that these are all unique textures. Let's make this a little bit taller even. And they continue across the edges. Now, if you just did, you know, a regular Voronoi and then tiled it, and I can kind of simulate this by putting this in a different position here, like so. So each one of these is now identical. However, the edges do not line up. So if you had a camera down here, you'd be seeing beneath your world. It's not what you want. So what we've done is we've created a way for you to do this procedurally. First thing you need to do is you've got your vector and you have W. So this has to be 4D. That's the first thing. We need to plug in our vector. And we can see something's going on here. We already get a little bit of stretching in strange places. Let's plug our W into the W. And now we can see, let me bring this in slightly, just so it's completely butt edge against each other. So we can guarantee that this is going to be lined up nicely. And you can see regardless of the density here, we're still pulling these through and all of our edges match, but each one is identical. We now have a tiling procedural texture. This works with Voronoi. It works with noise. Anywhere that you have a 4D texture that you can plug in your vector and the W, this is going to work for you. So now we have tileable Perlin noise. And this is useful because if you only had one tile that you were making, you can guarantee that this, if you then put it into a world where it is all tiled, this is all going to work. Perfect looping displacement. That's how you use the looping coordinates. Got to be with a 4D texture. That's how it works. Next one we've got on here is the mapping node. If you've used shaders, you know how to use this. If I bring back my image texture, it's probably the easiest way for us to show this off. We're just going to put our position in front, like so. And then we can plug in our image texture, set this to our texture as we had before. Let's plug in our color into the texture. Let me drop that down as well, just so we get the nice displacement. There is our texture. We now have control over the position, X, Y, and if it was 3D, then we would also have Z. Obviously for a texture, an image texture, this is immaterial. We have our X rotation, which we can see is going around the X axis, Y rotation, and the Y axis, and Z rotation, which is the one that's going to be useful for you with an image texture. And we have scaling X, Y, and Z. You also have the option to invert. So basically this is like turning it from point to texture on the shader version. And it's basically going to mean that when you move it, it moves counterintuitively. It depends what you're used to expecting, I suppose. But there we go. That is the difference. So it's going to invert all of your transforms. That is the mapping node. Now we have a few interesting nodes, which are a little bit different. The next lot of nodes, I'm actually going to group into one because we kind of have like a super combined node as well as the individuals. It just depends what you're after. So the individuals are Cartesian to cylindrical, Cartesian to spherical, cylindrical to Cartesian, and spherical to Cartesian. These are basically space conversions or coordinate conversions between, well, let's have a look at two of them real quick. So Cartesian to cylindrical is going to convert X, Y, Z to radius, theta, Z, or you're going to get the other one for cylindrical as well with the other Greek letter. There is a kind of supernode included. So we've got the space converter node. And this is really useful because it allows you to basically set from and to. So you can set 0, 1, or 2, depending on whether you're looking at Cartesian, cylindrical, or spherical. Why would you want to do this? Because it makes certain things much easier. For example, if I was to do something interesting with maths, if I'm making a circle, for example, and I want it to be moved in the z-axis by a sine wave, if I take my line node, if I think about a circle is going to be 2 pi, right? So I'm going to set my length to tau. Now I can see I've got this line going in the x-axis there by 0 to 2 pi. And I also want this to have a certain radius, so I'm also going to move it in the x-axis. So x is our radius, y should be our angle, our theta. So we can see that there. Now maybe I want to do something Yeah, something with the sine wave in the z-axis. So I can take my factor, multiply this by a certain number of pi. Let's go like 4 times pi. This should be 2 full sine waves. And then we're going to just put this through sine. And then maybe we can make it bounce, so we'll also absolute it, right? Something like this. Now, if I use a set position node, let's grab it, geometry, set position, and I grab a vector, combine x, y, z, let's move this to the z-axis in the offset. If I look at this, we need some more points. So let's grab our vertices and we'll just increase this up nice and high, somewhere around 200, so we can see what's going on here. We have a straight line which bounces in the Z. Now, if you were to make this into a circle, this is a lot more maths if we're working in Cartesian. This is where it gets useful. So in Cartesian space, you've got to do your X and your Y based on like sine and cos. And then you're also going to have to do your Z because of this. However, if we just say that this isn't Cartesian, this is cylindrical, and we want to output Cartesian, what I can do is I can just get this set position, right? Let's make another one actually. And I can now take my input position through here into my output position there. There we go. Now we're setting this position through our space converter. I'm saying that this is not Cartesian, this is actually cylindrical. So now what it's doing is it's reading XYZ, not as XYZ, but as radius theta Z, and then it is converting that to X, Y, and Z, which basically gives us this. We have a nice little surface now, a shape, a curve that we can work with. In fact, if I was to do something like maybe arraying these, let's grab a linear array, and we want to realize these as well, and we want to set our offset way lower, maybe even negative. You can see that we're getting some really fun effects really quickly. This is a really nice procedural way of working to generate lots of shapes. And let's say instead of cylindrical, we're working at spherical. So now instead of Z, it's going to take that as, I think it's phi, which is your polar radius, your polar direction. And now suddenly you can see that we're getting this really interesting shape. So you can do all sorts of things, and you can obviously convert your inputs and outputs separately. Do something like this, have loads of control, and you can do these one after the other. Do lots of different conversions, control different stuff, twist your universe through itself, through different coordinate spaces. Amazing. Damn. Always get really excited about this one because it's kind of like using curve formulas in Spirograph. So you can build this up nice and easy. If I want to have more control over here, I can basically say multiply by pi. This is the number of bounces that we have, and then the integer that we multiply by is going to be basically that value. So now we're going 1 bounce, 2, 3, 4, 5, 6, and you can set this however you want. You can multiply this down now, do all sorts. We are interested in masks. Got a camera cull mask here. So this is actually one of the first nodes that I made in the original toolkit. Very useful node. I can paste my driver into here. So this is my field of view. And we're going to be outputting a mask based on the camera region. If I add a grid, something like this, let's make it a bit bigger. Let's do a point, distribute points on faces. And we're going to instance on these points, just something simple like a cube, like so. All right, let's make this smaller on the scale, just so we have something to look at. Nothing too fancy, just gives us something to work with. Where do we plug this? Well, if you're using it like this, you can just plug it straight into the selection. That's the easiest way. You can plug it into a delete geometry, but you would need to invert it. Remember that you're deleting the selection. So it's just going to basically need to use like a Boolean math set to not, and that's going to invert it. You can see I'm removing that from our thing. Set your resolution, make sure that's all fixed up. I use drivers for my field of view just so I can control the camera later. And we also have the padding control just so that you get a little bit of buffer. For example, if you're right close to the ground, or if you're moving around big bushes, it can be useful to have a bit of extra padding just so that stuff doesn't pop in front of the camera. We can extend to the camera, which will just bring it down to that Z position as well, just to make sure that you don't have any foreground popping as well. Now, if I'm in camera view here, let's set this back to 0. You can see, as far as the camera is concerned, everything is visible, but we are only viewing a very small percentage of our entire scene. Camera cull node we will come back to a little bit later because it's also used with the foliage node. Now, distance culling. This is the next one. Again, I'm going to pick the camera as my distance cull. This doesn't really matter, but just in case you want to do that, we're going to set a distance with a little bit of fall off here. So actually what we have is essentially a radial distance, something like this, and a fall off control. So if I set this to 0, we have a hard edge on our radius. You can see that there. And if I increase this, then we just basically add or subtract various points within that radius. Just gives you a little bit of smooth fall off. If you're doing levels of detail, this can be a useful way of working. Basically instance some on your inside points, instance some other ones on your outside points, and there we go. So that's a nice way of working with LODs in a kind of very simplistic way. We also have an SDF on here. It's essentially creating a sphere SDF, so it should be negative on the inside. So all of the masks, aside from the camera, I think, although I may update that in the future, has an SDF, which is essentially a signed distance function. So let's grab, I'm going to add another object. I'm going to add a monkey, just because it adds a very useful 3D shape for us to compare against here. This is going to be for our points inside mesh, right? If I just come in here, let's generate a grid of points, 3D grid with ETK grid. Let's make this a little bit bigger in each axis. Something like that is fine, maybe even a little bit bigger. And we'll also go for more points. I'm going to go quite dense. Something like that is fine. Now I want to bring in my Suzanne object. Let's set this to relative. And I'm going to mask this with a points inside mesh. This is our mesh, our Suzanne. And we have either fast or full. You'll see the difference for that in a moment. There's also an option for a backface check. And again, you're going to see the option for that in a minute, why that comes in useful. Now this is our mask, right? So let's grab instance on points. It's probably easiest. Let's grab the cube, just so that we have something to look at. Nice and small in here. Something like this will do. There we go. And let's use fast as our selection. All right. Now just so that we can see things a little bit better, let's grab Suzanne and make her wireframe under here, viewport, wire. There we go, good. So you can see that we have Suzanne basically masking out our points. So you can see that in here. And each one of these points, even if I randomize it, right, so it looks nice and freeform, she's just generating those points. Now, there is a different accuracy. So this basically, if you were to do this with a cone, you would really see the difference. But essentially it subdivides the input mesh just to give you better accuracy, but at the cost of speed. We also have full instead of fast. This will be about 4 times slower. I'm not sure how this would perform on a very heavy mesh, but from my tests it's been pretty good. So full will do a complete check, left, right, forwards, backwards, up and down. Fast will only do forwards and backwards. It's raycasting, by the way. It's just checking whether or not a point is inside the mesh. All right, there is also a backface check, which we're actually seeing reduces some of this accuracy here because we have some back-facing stuff going on inside the face. If I remove this and let's go for a collection instead, just so I can show you why the backface check is so important, just drop this into my extra collection. I'm also going to grab a cube, which is going to be wireframe as well. So let's use our hidden collections, just separate, there we go, into our mesh. And I just need to realize those instances and we're good, all right. If I just make sure to put my cube into that hidden collection as well, there we go, we can now see we have points basically, all of the ones which are inside the cube, and also all of the ones which are inside Suzanne. But if I backface check, and the issue is that all of these ones here that should be inside the cube, it checks and it hits the front face of a Suzanne. So while the backface check does make it generally more accurate, for example, I would recommend doing this inside something where you have a lot of very complex geometry and things may be inside nooks and crannies. So the backface check is great for that. However, when you have intersecting geometry, it actually causes issues. So that is off by default, but it's there if you need it. And yeah, this can be a really fun way of masking out points. Let's have a look at the selection box node. This is kind of what it says on the tin. Plug this into the selection and you've got a box. Nice and simple. Let's make this a little bit denser so we can have a look at some more of the settings on here. If I make this taller, we can see we have a taller box. If I rotate it in the y-axis and then the z-axis, x-axis, you can see what's going on here. We essentially have a box which we can move around and it makes a selection. We can also round the corners if you want a more sort of lozenge shape. So that might be useful for some of you. Now we also have the SDF, right? So anything close to the surface is going to be smaller, or sorry, have a lower value. and it's going to get bigger towards the middle. So again, might be useful inside and outside. This is the control for each one of our selections, right? We have a cylinder selection by normals. This one is going to not work for us here because we don't have normals on our grid, but this is going to allow us to distribute on a particular direction. If you're used to the previous version of the toolkit, this is ETK steep. So it basically allows us to position foliage and things like that based on the normals of the mesh beneath it. Use the inside, set your normal direction, and you can set deviation range. The factor as well, this is essentially like an SDF, but 0 to 1 based on whether or not things point in the same direction or the opposite direction to your input factor. The other masks we've got in here, prism and sphere. Sphere is the most simple one. It is essentially just a sphere. There we go. Nice and easy. So that's all of your selections. We do of course have the other shapes, but they are literally just other shapes. Plane is up or down of a particular plane, which has a normal and a center. So this can be useful for doing just kind of left or right of a selection plane. Alrighty then, we have made it to the final category of nodes. We've got through all of our masks, mapping, generators, fields, fall-off and curves, and we're now onto the utilities, which are essentially the useful ones. You're going to use these ones much more than any other in the pack, certainly some of them. Let's start at the top here. We have align mesh by mesh. This is basically a straight rip of a node from Spirograph, very useful node. It allows you to very quickly align a mesh by either 0, 0, 0 or another mesh. Let's grab just a regular cube. This will be fine. And I'll also grab a cylinder. So I'm going to be aligning my cube. So this goes into the geometry. Have a look at the output here. So if I just mute this, we can see this goes back to 0. But by default, we are aligning the Z-axis, which is why it moved up. This is all the way to the left on our G. This is our geometry. So we are aligning the minimum of our align axis to, in this case, the maximum of our target. Now, when nothing is plugged in, this target is just 0 at 0, 0. So you can see if I move this, so right now it's on the bottom, we can move it to the middle, there we go, at around about halfway, or we can move it to the top. There we go. So top, middle, bottom of the axis. And you can do this in the Y or the X as well, or multiples. You know, if you want this to go in all 3 axes, then you can do that. Or, you know, you can use these in series to do different alignments on different axes. So let's just do it with the Z for now, just keep it simple. And I'm also going to take my cylinder. Let's join these ones up just with a join geometry. And I'm also going to plug my cylinder into the target. So now you can see I might want to put the bottom of my geometry onto the top of my cylinder. Now, if I wanted to go onto the bottom, let's go into wireframe mode here. I could set it to be aligned to the top of my cube and the bottom of my cylinder. So this means basically that we are able to manipulate things really, really quickly and really, really easily. Next one on, we have got array linear. We touched on this one before, but essentially it is going to allow you to do a linear array, basically aligning down a line. Now by default, we have the count, we have a start position and an offset. So this is like your basic array, and we can always move this, let the start position wherever you want this to be. I'll leave it at 0, and we can leave the offset to whatever this is going to be, right? So we can set this to an offset, and you'll also see that the offset says /end. So if you tick the box which says use end, then now this actually works as a line segment. So in a lot of cases, you may want to array between 2 points and say, oh, I don't know, have 20 different instances between 2 points. So if we do this and we move these around, have something like that, and let's bring this down a little bit. There we go. It's a little bit easier. Now, maybe you want to actually use spacing instead of have these controlled by the count. So we can also turn on spacing, and that's going to work. You have to use end if you're going to use spacing. That's just part of how this works here. Now we can also set it to a line rotation, and you can see what that does. We basically have these being aligned to the axis that we are moving this on. There's no locked pivots, so we can get some weird rotations, but for general stuff, this can actually work quite well. So that is how we use the array linear. It's quite simple. It's basically like a polished version of the array modifier. Array radial. This one's very useful, of course, because if you have your object, let's use our cylinder again. We can just drop this through our radius. Now we can set a center on this, so you don't need to do a separate transform to move this, but we have a control for our radius and our count, and it's not going to be particularly noticeable with our cylinder, so maybe I change this out for a cube just so you can see. But we also have the align rotation on here, which is going to align it radially like that. Now we can also use spacing, which will override the count, and that's just going to allow you to do something like this. Have it set based on your radius, so you have a number with a decent even spacing. Of course, when you have more points, you have a more accurate spacing value. All right, on to the next. We are looking at the array spline. Plug this onto our geometry and have a look. Now we don't have a spline plugged in. We can either use a custom one, like, you know, generating an actual curve in the 3D viewport and just plug this in through your object info, or we can generate a spline. So let's go ahead and use a curve primitive. Quadratic Bezier is going to be probably what I want, just to keep it simple. And let's move these out a little bit. Get these rotating up. Right, so align rotation is on by default with this one, and you can see that that is following the curve nicely. Also worth noting that if I stick on a curve tilt node, that we are tracking the tilt as well as the tangent. So we have two align rotations going on here. Now we can set this whether we want spacing or count. Nice and easy, and it's just going to use the resolution. So this is going to allow us to control the resolution of the curve. If we have a custom curve especially, this will be more impactful. Utilities. Attribute to instances. The attribute to instances node allows us to do something like take a grid and let's instance our cubes on this grid. There we go, we have 9 cubes, looking good. Let's put our attribute to instances on here. And I'm going to go with this grid. I'm going to plug this into my target. Now what's happening here is it's going to generate realized geometry. These are no longer instances at this point. They're real geometry. However, they will have taken on an additional attribute, which is correct for these. Now what could this be? Let's take the position, just so that we can see what's going on here. If I plug this attribute through to the output, just so that we have it, we can debug this inside our shader. You'll see what's going on. Let me just call this one pos, just so that we can call it in the shader. Let's grab our shader editor, find a new one in here, and I'm going to find the attribute node and call pos. There we go. Let's take that vector across to the surface, and we'll just go into EV. Now, right now, nothing's happened because we have not really assigned a material. So let's go material, set material, just grab that in here. So right now it's all black, and this is because we don't have an attribute coming through. And let's just plug this through input position, plug this into our attribute. And now we can see that we have these values. Some of these are negative, but that is fine. Right now it's going to choose between nearest face or nearest. If you have a point cloud, then you want this to be ticked on. If you don't have any faces, this needs to be ticked on. Otherwise, like if you're transferring normals or something, it will interpolate it from the nearest face. So what's the difference between this being position and just a regular position? Well, the regular position you can see has Z values and it's different across each point of the cube. So using this way basically transfers the attribute from the grid, from this grid as the target, to our instances. It turns them into real geometry. If you need multiples of these, as sometimes you will, for example, if you're making the position transfer across, but you are also transferring something like the index, you just make 2 of them and you can use the attribute directly like this. So let's call this one just A, and instead of position, let's use the index or something like that. So now we'll actually have like an instance index. And if I call this, we can see 0, 1, 2, 3, and so on. Let's have a look at the bounding box. The bounding box is a default node. This just gives us more outputs. So if we had something like a sphere, you can see that we end up with a bounding box that fits the sphere. But our new bounding box node does the same thing. So we don't have the min-max vector anymore. I've always found using that node that I've never actually used the min-max vector just straight. I've always used it through some kind of like separate XYZ and map. So that's what we've done here. We have a vector for the center. This is not the average of the vectors, this is just the central position. So for this it should be reading 0. And then we have like the minimum x, maximum x, min y, max y, same for Z. And we also have the size X, Y, and Z. So if you just basically subtract one from the other. So if you ever need specific values from your bounding box, this is the node that can do it. Often there's things like size is very useful. If you use this in combination with the brick straight nodes, this is going to allow you to set your brick size from your collection. Nice and straightforward. Utilities, copy on points, right? This is the one which is like the attribute to instances, however, a little bit more feature rich. Essentially, I know it's a really big node, so it can be a little bit daunting, but we take our points, we take our geometry. By default, we can see this is looking just how it did before, but we do have some extra options. So this is also combining the instance on points node, hence the selection and pick instance option, which will help you if you're doing collections, so foliage, stuff like that. Instance index as well, that's very useful, but again, just a default option on the instance on points node. And the option to randomize the instances, this one is actually not a default option, but something that you will notice if you have a collection and you instance it on a regular grid like this is, for example, if you have 3 items, it would go 0, 1, 2, 0, 1, 2, 0, 1, 2. The randomize instance option is going to randomize which point goes where. So just lets you distribute your scattering a little bit easier just on there. All right, now we also have rotation. So again, this is kind of a default thing. What is not default is the deviation. So if I set my Z deviation to 360 degrees, now you can see that we're getting 360 degrees. In fact, I only need to go up to 180 because it's going to be positive and negative. It's kind of like an epsilon, your bracket, right? So we're going to add 180 degrees and subtract 180 degrees from our target rotation. So if I set all of these to 180, we have complete randomization. Equally, the scale works the same. First scale is just like our default one, and the deviation is going to allow us to randomize this. If you want things to scale evenly, just tick the even scaling box and you'll be golden. Seed, of course, just does what a random seed does. Now, the outputs are where this actually gets interesting. So set these back to 0. So this is where this comes in very useful for making things like flowers, because if I plug in my local position, you will see that we have that local position directly. If I plug in the index, then we have like 0, 1, 2, 3, 4, 5, and so on. If I plug in the rotation, right now it's all 0, but for example, if I set the deviation higher, you can see that they're pulling through the actual rotation, the total rotation, which can be really useful if you're doing something where you need to know the current rotation of your thing so that you can essentially unrotate it, manipulate it, like doing bends and things like that, creating folds for your leaves, and then reapply that rotation as a flat value to your whole thing. So if you're doing this with a rotate, vector rotate, set this to invert, set this to Euler, you've got your position. This is going to be your vector because that's all the vertex positions. Your center is going to be the local position. Your rotation is going to be the rotation. Then you can do whatever you want to do. And then you just have another one of these coming through, set to not invert. And that's essentially going to allow you to modify this in the middle with a proper transform on the individual things. In this case, I'm going to assume you're using this for petals. This is like your flower making node. This combined with Phyllotaxis, this is it's gonna save you a lot of time. That rotation plugs in there, and your golden, you can see that's all set up nicely. So a lot of stuff you can do with the copy on points nodes. It basically just transfers all your attributes directly. Nice and easy. Next one, displace noise, texture, and Voronoi. These three are basically more or less the same node, just with slight variations. Obviously, the noise one looks a little bit bigger, and we've played with the texture a little bit earlier when we were looking at the mapping nodes. But essentially, you can plug in an object like a grid. Let's make this a bit higher res. This can come through, and we're just going to be displacing that surface, something like that. So we can choose whether we're going normal or vector. Vector is going to be using RGB noise to control the direction, and you can always multiply that by a certain thing to go in a certain direction. If you want it to only go in the X direction, for example. So normal is what it's set to by default. The strength is going to do that. The mid-level is going to do that. That's all kind of standard stuff here. And then we have controls for our actual noise. So with no noise coordinates plugged in, it's just going to use the position. But of course you can manipulate this. You could use something like some really interesting converted space coordinates, something like putting in the position through a space converter, plug this into your noise coordinates, and now you have all sorts of weird things that you can do with creating different types of noise. Interesting. So by default, this is just going to take the position though. We can set the detail, the roughness. It's just a noise node, right? It's just taking all of the noise values, putting it onto the displacement with some displacement control at the top, in the same way that the Displace Voronoi does a similar thing, but we don't have the RGB, so this is just going to be doing it in the normals, just like that. Strength, mid-level, scale, and randomness. This is just using the distance of your Voronoi, and the Displace texture is going to allow you to plug in any texture, including the default ones. Like if you wanted it to be, I don't know, like the brick texture or something, there you go, you have something like that, and that's going to work directly in there. Equally, the noise, if you're using 4D noise so that you can get your looping coordinates through it, you can do that with the Displace texture. Again, strength, mid-level, normal versus vector. If you set this to vector, then you can do the offsetting. So for example, if you wanted a specific offset vector for a Voronoi, then the easiest way is to do it through this Displace texture like this. All right, so that's our displacement. They're just like the Displace modifier, just rolled into a single node. Now let's have a look at Foliage. This one's a nice big node for you. Let's grab our input geometry. Do you know what? I'm going to make something a little bit more interesting here. I'm just going to pull this one in to my node tree, and I can actually now just hide it. That's fine. We have it now in the node tree, so that's good. Set it to relative. Let's smooth this one out with a subdivision surface. Maybe I even put a noise displacement on here. Utilities, displace noise. There we go. All right, we have something nice and lumpy for us to work with. Now, the Foliage node actually expects geometry. So not points. You don't need to do a point distribute. That's all going to be handled by the Foliage node. We are only interested in the actual base geometry. So plug this one straight through like so. And I will also just add a join geometry afterwards. There's a lot of options on here. We're just going to work through them nice and easy. Now we need a collection to distribute. This is a little bit different. Rather than generating stuff in the node tree, this is really mainly useful for using assets. So for example, if I add some grass or plants or something, I'm going to use these spiky ones. We just need one or two in a collection, and I'm going to hide that botanic collection. Let's go in here. So we have a load of plants on here, and it's running a little bit laggy, right? So the first thing we might want to do is plug in our camera cull mask. I'm first of all going to need a camera, so let's go ahead and add that to begin with, and I'm going to add my mask camera cull. I'm going to select my camera object, and we're going to just plug this into the camera cull mask. Everything's set up as defaults, right, with the default 50mm lens and the 1920 by 1080. So this is actually working absolutely fine by default. We can see that this is now nice and fast. If I hide that again, you can see running to a few little draw issues there. In fact, if I increase my viewport density to 10, we're really losing. Oh, it's like walking through mud. Turn that on, nice and fast. All right, now this shouldn't really affect render speed if you're rendering with cycles, but it will make a slight difference when rendering with Eevee, or of course the workbench while you're working in solid view. All right, camera culling, check. So you just plug that one straight in. Now you may also want to be using a selection, so you can plug in your selection there. You're probably interested in what the viewport density, render density is. This allows you to switch. So for example, if I say that I want this to be re-rendering at a density of 30, well, even with camera culling, this is not playing nice. And if I go without camera culling, this is essentially unworkable at this point. So if that was my render density that I wanted in my final renders, I can't work like this. But if I work at 10, we're good, we can move around, and I can set this into my render density. Now if I wanted to check it, I could still click on use render, but without that, this will just render the full density. I could even go lower in my viewport. And now we have completely smooth. We know where things are going. We get a sense of the scale of things, but we don't need to worry about the final density. That'll just show up in the render. All right, we do have the distance min as well. So by default, this is set to 0, just so it's essentially the same as a random distribution. But I can also increase this. You see, as soon as we start culling these, it does take a little bit more time. But if you have trees or something like that that you need that Poisson disc, you've got your minimum distance there. Seed as well does what seed does. Now we also have normal masking. So this is going to be useful if you don't want stuff, for example, growing underneath an overhanging surface, or if you just want stuff on your Z facing. So right now the angle deviation is 180 degrees. Let's reduce this somewhere like 30 or 40 degrees, 45. So now we can still get stuff on slopes, but it's not going to be on sheer surfaces or overhangs. And you can change this if you want something which is specifically going to instance on like an upside down surface. I don't know, maybe you're doing roots or something instance below a cliff, then you could set that to -1. I'm just going to go with 1 at the moment, 45 degrees. And there we go. Now we have our rotation. By default, we can see that we actually have some rotation and scale deviation. So default rotation is set to 0. This is fine really. And our deviation is set to basically rotate and tilt stuff. We can also set whether or not things align to the mesh normals. When it's off, everything just points up. When it's on, things follow the surface. Scale as well. By default, this is 1, deviation of 0.2. Otherwise, things just look quite regular. All right, so that basically covers the node. One other thing that you may want to do, I know this has been raised on Discord by a few people. If I set my scale deviation to 0, I can now use a node in the utilities, which is the random bias, to set my scale. So for example, if I plug this in, and let's say that I want my scale to be generally 1, so I'm going to set this to be 1 actually in the min, and then for my maximum scale I'm going to go for 2, but I'm going to bias this now towards that lower end. The majority of these are going to be lower. It's basically using a power curve, right? So now the majority are going to be lower, and you'll have a few which are bigger, right? And we can see that here we have some showing up big in our viewport. The majority are a little bit smaller. Maybe if I make that even more obvious, you can see the majority there's a little, but we do have some that are just considerably bigger. So the random bias, that is the node that is going to allow you to do this. And you just plug it in and turn off the internal deviation. All right, so that's ETK foliage. It's a big node, but it does everything. It does everything. If you're making foliage, this is the one node that you can do it with. Otherwise, you gotta, you gotta set up some stuff. Right, foliage, force, size. This is one I don't use enough. We have a fairly big object here. I'm not quite sure how big it is, but it's definitely quite large, around about 28 meters, maybe even a bit bigger. So if I take this object info node, which is our object, and I can now force the size of this into being 1 meter, or let's say we're going to make this 2 meters. You can see that it fits perfectly now into that 2 meter by 2 meter grid. It basically just takes the maximum size and scales the whole thing down evenly until that maximum size fits within our threshold here. So if you have something and you've made it to maybe an arbitrary scale, ETK force size is going to allow you to, well, force the size. Basically just sets that maximum size and scales everything down nice and even. Next one, LODs. All right. This one, it does allow you to basically set up an LOD system based on the distance from a camera. So you'll want to plug in your points, essentially distribute points on a surface and then plug these in here. If you're rendering with cycles, this is not actually, it's not going to help you. Cycles handle instances perfectly. You don't need to be loading additional instances. It's actually going to be slower, but you just load in your camera and then you say what your high res one is for LOD 0, and then your second LOD, third, fourth, and you can set your thresholds for different ones. Now, if you want everything to be low res, if you're just doing like test EV renders or something like that, you might want everything to be lower. So you can just click this tick box. Everything is going to be forced into LOD 4, in which case it's all going to be the low res instance. And again, we have controls for the rotation and scale as required. So this one is kind of an odd node. I know some people do use it quite extensively, but if you're rendering with cycles, you genuinely do not need LODs. But for EV or workbench, I can understand why you may want that. Let's continue. MatSmooth, it does two things. It takes your geometry, like a a cube, something like that. And by default, it's going to set shade smooth. And we can also set a material on there as well. So we can see the smooth shading and the material set. Just does it in one node. Commonly, this is something which is useful to have just at the end. You know, you've made your thing, you just want to assign a material and shade smooth real quick. Or if you've done something like curve to mesh, you might actually want to untick shade smooth and apply a material. So just does it as one node, nice and easy. Mesh boundary. This one is an interesting one with questionable utility. I've included it because there was one specific use case and somebody needed it for that. If we have a mesh, like a grid, for example, let's make this a little bit bigger, maybe 5 by 5. Maybe we can make this a bit smaller. Cool. All right. So the use case is you have background hills that you've made procedurally with noise. But when you look down at these from your main camera vantage, you've got the edge of this mesh being really high up and obtrusive. It's in the way. You don't want to see it. We want this to kind of, you know, gradually fade down towards where the camera is. This node allows us to basically do this towards all of the mesh boundaries, and I'm saying this with a caveat. This is using a convex hull node, so it's not going to work where you have an in part of the land. If you have like a mesh which is something like this, we're only actually going to be measuring the distance from the outer boundary here, not this inner part. That may make this not very useful in all cases, but certainly if you're just generating background hills, this can be very useful. So the use case basically goes like this. You have your hills, and if we set the position and we take the position input with a vector math and we multiply this by 1, 1, and then something else in the Z, we now have a control for the height. And more than that, we can use the fall off from our mesh boundary to control the Z position, right? The Z value. So let's grab a vector, combine X, Y, Z, plug this in here. X and Y go to 1, and the Z is going to be our fall off. All right, so this is already looking pretty good. If we want a bit more control, let's go ahead and use a map range, something like this. And we can now control the distance of that fall off and things like the interpolation. If we want that to be a bit different, we can actually just go off the distance, which is sometimes more useful because you have that, you know, real fine control for that. But you can see that things are happening at the top as well. So the issue here is that, let's have a look at the debug. We've got the full mesh. We want this to only really be our outer edges. We want to limit this to just these 4 walls, ideally. Different meshes will give you different outputs. So just use the debug to check where these are. And now you can see we don't have any weirdness going on at the tops there. We can just control this like this. And now you can see, you know, if this is your horizon and you've got all of your foreground here. Now this is much easier to look at than this was, where you could see below that mesh. So there we go. That is how we can use mesh boundary. I know it's a bit of a weird node, very, very specific use case. But if you ever need to find the edge of a mesh by its kind of convex hull, this is the way. All right, mesh to instance. This one is very useful. If, for example, you've generated a whole bunch of things, let's grab a cube and let's grab an icosphere. If you've got all of these, right, and you want to be instancing them all together, and let's grab a grid as well. So we'll instance these on top of a grid. Point, distribute points on faces, instance on points, and let's just grab a cube, right? Okay, nice and easy. Right, what happens if we want to also instance the icosphere, but we also, you know, we want to pick it. We want it to be, well, pick instances. I can just use this join geometry, can't I? Well, unfortunately not, because now we're actually instancing both. If we go to wireframe, we can see that they're both there. And indeed, if I joined all of these together, it's just instancing all 4 of them everywhere. If we click on pick instances, they disappear, and the node gives us an error that says realized geometry is not used when pick instances is true. However, utilities, mesh to instance. Now we can basically just do that. It just turns your mesh into an instance instead. This is no longer realized geometry. These are instances. It's a very simple setup. It instances it on a 1-point line. That's how it works. And there is a little option in here to reset the position. So for things like the cone, which is centered on 0, you may wish to just center those. and it just centers it on 0, 0, 0, basically. So this is how you can use the pick instances with generated geometry. You just need to use the mesh to instance node, and you can do whatever you want. This is how I generate my large scenes with lots of different generated geometry and still be able to instance them. This node, mesh to instances. Who is up next? We have got MixFloat. Oh, this one's very simple. It's kind of like the color mix RGB set to mix. These are essentially the same, but instead of colors, it's just working with float values. Sometimes this is more useful. It's very slightly sort of computationally less intensive. Allows you to just lerp between value 1 and value 2. Very simple node. Next up, we have got point distribute. All right, this one's a little bit different because this one has the viewport and render density built in, and these are fields as well. It's Poisson disk, but these are fields. So we don't have the whole like density factor thing going on. It's just a straight field directly into the density. You've still got the distance minimum for setting up your points. In fact, I can plug this on to here and we can check the points. So I can set my viewport density. I can change whether or not I have a distance min control on here. And if I want to have lower density in my viewport, higher density in my renders, then I can do this nice and easy. We have a selection option as well here, and we'll still pass out the normal and rotation per point. So nice and easy. It's basically just a nicely polished version of the Poisson disk node. Just sometimes you want that instead. Sometimes you want that render switch. After point distribute, we have random bias, float, and vector. We talked about these before with the foliage node, but essentially we set a minimum and a maximum, and then we can bias the probability towards one or other. It's just following a power curve, but that is how this works. Very useful if you're doing foliage or rocks or something and you want 90% of them to be pretty small and 10% of them to be pretty big and have that noticeable variation. There we go. So that's the same whether you want it for vector or float. That is what the F and the V stand for. We then also have random float and random vector. These are bipolar, meaning that they add and subtract from our target by the deviation. They basically work the same, right? But I'll just show you on one for now. If I wanted my values to be between 0.8 and 1.2, which is pretty common for foliage, I would set my value to 1 and my deviation to 0.2. So now it's going to be 1 as like my target, and we're going to go sort of 20% below and above. Now this is really useful because if I actually decide that I want to set this up to 2, because maybe my foliage assets are a little bit smaller than expected, we still have that deviation. We only have to change one thing. If you use the random value node and you wanted to go from 0.8 to 1.2, and then you're like, oh, actually, no, I want to go from 1.8 to 2.2. Well, now you have to type that in twice rather than just controlling one value. So I generally find for most of what I do, the value and deviation, this is how I work rather than the min max. So this is why on almost every node, except from the random bias, you will find value deviation or vector deviation rather than min-max. After these, we have got the render switch. So this one's very useful. Essentially, this is what does the switching. So we can use this with any nodes. So this is why we've made this into a separate node. If you want to distribute points on faces with a grid, we have a bunch of points. Maybe we go for a higher density on here. And maybe we have two different densities. We have one for our viewport and one for our render. That's what we can use. So I can plug this in here. Maybe render is 100, viewport is 1. You can see that will switch. As soon as we hit render, it will use the render value. It's based on the isViewport switch. But the great thing about this doesn't just work on distribute points on faces. It works anywhere you need a value. So let's say we set this to 5, but then we have a very high resolution version for the actual render. That's one way of using it. Or you can even use it with a subdivision surface. So we have a regular number here. And let's say we're going to set this up to 5 at render, 2 in the viewport. Do it like that. So in the viewport, we're going to get 2. When we hit render, we're going to get 5. So you can see how this becomes very useful. It's kind of like in particles when you can set the viewport amount. In particles, I think it's like a ratio, but I prefer to have like an explicit use this because it allows you to use it in more places to specify a specific number of vertices, number of subdivisions, number of density, whatever you need. Moving down, we are so close. Shrinkwrap. This one's a bit interesting. This is the first one I think that has an alternate green socket. So let me show you what this does. Shrinkwrap, if you are not aware, allows us to, well, shrink-wrap, do something. We have a Suzanne still. Let me move Suzanne down a little bit, just so that we're below the surface. Something like this. I know it's wireframe, but you'll just have to bear with me here. So I can pick Suzanne as my target. That's fine. And we have an influence of 1. This is a field, so we will get onto that in a moment. I can now do something easy like geometry set position. Position goes into the position, and there we go. So we can see that that all moves down. Essentially, it's shrunk wrap based on the direction. We can use a different direction based on whether or not we need to shoot in a different direction. And we can use opposite. So for example, if I move this up, we can see that this is always going down, right? But if I use include opposite, what it's going to do is it's going to use the closest, whichever one is closest, up or down. And you can see that that moves between them as we go through that. Why is this useful? Well, because it means if you have something like this, we can shrink wrap a surface to another mesh, which can be very useful. And we have this influence. So why would you use influence? Well, let's say, for example, you're doing the beach and you want your sea to roll up your beach, but you don't want it to be always attached to your sand because that's going to be going down below the water. So you would use something like the position with a separate XYZ and a map range on one of your axes. Let's go with the X-axis. So map range, this can go into our influence. Maybe I set this to smoother step so that we get some fall off, or you could make this a 0 to 1 range, put it through one of your easing nodes. So this is going to give us something like this. And now you can set, a certain distance where you have your influence 0, influence 1, and you can imagine why you may want to have something like this, just so that you can roll your water up the beach, something like that. There's a green socket here next to our target. So this says alt next to it, meaning alternate. And that's basically what it is. Even if I select Suzanne in here, if I were to go and add a UV sphere, let's also add a transform node, plug this into our alt, and let's join this on after our set position just so we can see it. So as long as we have something in our target, it's going to ignore the alternate target, right? Maybe I make this a bit bigger and move it down, something like this, all right? If I don't have something in Suzanne though, you can see that we're actually going to use this. We're still taking into account our influence, but there we go. That is allowing us to have a little bit of procedural control over our mesh. There we go. Can get rid of that. And you can see this is now following our UV sphere, which is going into the alternate target. So it's just whether or not you want an object picked, like an actual 3D object, or if you want the green one. I know I could have done this just through an object info node. Sometimes I did, sometimes I didn't. I just thought sometimes, you want to just grab this and use it. No extra nodes needed. Sometimes it's just more convenient to have it on the node. All right, so that is shrink wrap. Next one we have is stepped transform. This is one that is coming back from previous versions of the toolkit. Now again, we have instance collection, which is, optional if you want to do a collection. And we have an instance geometry alternate. So this time we're going to use the alternate again. Let's use a cube. So I'll use this as my instance geometry. My points are going to come from, let's use a circle node, nice and easy. So just going to use ETK circle on here. Let's view the output. Let me hide Suzanne. So we have our points coming around nice and straightforward like this. And maybe we can just make the radius a bit bigger. So previously with the older versions of the toolkit, you had to plug in your size, your index and your factor through to the node. Now everything is handled inside the node, so it's a lot easier for us to use. It doesn't mean that we have any less control. So we can still plug in a custom factor. So you may want to do this if you are using FALLOFF instead. So for the Phyllotaxis node, you have FALLOFF. For the Spirograph node, you have FALLOFF on here. In fact, if I plug this in instead, then you will see that. Let's go for a slightly larger major radius, a way lower count here, maybe 20. There we go, 30 is fine. And instead of these rotating per index, which is what will happen by default, so let's rotate these in the z-axis. You can see that they're essentially moving along. So we're setting the per step transform for each of these. So each one along the index is going to get the next one of these counts. If I turn off per step, then this is the value that we get by the end. Easier for me to demonstrate this with a line. Plug this in like this, and we're going to grab use spacing. Use 10 of these. So if I have a 90-degree rotation in the x-axis, then you can see that by the end, we've got 90 degrees. And if I set this to per step, we don't see it because these are cubes. But if I reduce this, let's go for like a 10-degree rotation. Now you can see that we're getting that rotation per step. We can also do a translation and a scale. Let's go for like 1.1 or something. So we're getting a little bit wider, 1.5 maybe. And this is a linear increase. You can turn this onto compound scaling if you want an exponential increase. A lot of stuff you can do with this. You may want to use this with something like the brick walls with your custom factors coming through. So that's somewhere that you might want a custom factor because you have a grid and you're using it points across, or maybe you're using it with a grid, generator grid, and you're using one of the X factors. Rather than going up to a value of 1,000, we should now be going up to just a value of 10 on the far side. Turn off compound scaling, set it to per step. This allows us to use the custom factors. And now you can see, because we're using the custom factor, it's moving them all across from X to negative to positive X. Without this, you can see that it's moving them by index, which is going along in a kind of zigzagging way. Equally, we could use this with just the Z factor, the Y factor, the X factor. So you can see how this becomes a really fun tool. It's kind of like the Cinema 4D MoGraph stuff for advanced array management. Using the generators in here with the step transform allows you to do some really fun motion graphics. We have a couple of more advanced switch nodes. Switch geo, switch object, switch vector. These are all much of a muchness. These basically allow us to pick by index rather than just ticking. So you can have up to 10 things in one of these, plug them through. In fact, if I just show you with a few different options, something like this, right? And I can just plug these through. We only have 0 to 4, but you can see that if I now change the index, we're switching between each one of these as needed. Essentially does the same thing, switch geo, switch object, switch vector. They're all just the same, allows you to pick by index out of 10 options, rather than it just being 2. Just a little bit more utility for you. Just before we touch on the UV lattice, which I think some people will be interested in, we're going to do the vector inject. This one is super useful. This is like the vector rewire in Spirograph. It lets you replace a channel of your vector. So for example, if I take a sphere, like an icosphere, and a geometry set position, here we go. Right now, all of the positions on these are basically on the sphere, right? These are all of the positions. But I could set the position, if I take these vectors and I inject a new value into all of the x's or all of the y's or all of the z's, then suddenly we can get a projection. So for example, if you have like a whole load of different positions and you want to like just set a specific z value, which might happen. So you might have a grid like this, and if I randomize all of the points, right, we have this just mess of points. But you might want to set just a flat z, or you might want this to be something specific like 1, or because this is a field, you could even set it to something like a noise texture directly, right? So now you've got still the original grid points, but all of the z values have just been replaced with some noise instead. If I make this 2D as well, it'll be even more obvious. We can see that we're getting that noise scale. Nice, good stuff. All right, so that is how the vector inject works. It basically takes your x, y, z vector and it lets you choose x, y, or z, or, you know, a combination of all of them, and replace those values in your vector with a set value. Whether that's a field or a constant is completely up to you. We have one more node to look at, and this is the UV lattice. This is not what I would consider a finished node, but it does allow you to do some interesting stuff. So what we need to do to set this up, I'm going to actually make a new object. Let's use a monkey, and I'm going to use a plane as well. So it's important that I use at least the plane in 3D space. All right, so I'm going to call this the plane. I'm going to rename this to controller. And what I'm going to do is on Suzanne, I'm going to make a new material. I'm going to just give it a new image texture of a face. So I have this image of a face, just a standard UV unwrapped face. You can use it for anything, but you know, for doing a face, this is kind of what you're after here. Now by default, I've got this just plugged into the UV map. And if I look at this in Eevee, we can see that that is not lining up very cleanly. The UVs for Suzanne don't really line up for this. We're not going to use Suzanne's UVs. We're going to be using some custom UVs. So let's grab an attribute node in our shader, and we're just going to call this one UV. I will make sure that I'm outputting this attribute momentarily. UV, we can see everything's gone black. This is what we want. And this is the full setup here for the shader, just our texture that we're going to be mapping, and UV, here we go. Now on Suzanne, I need to give her a geometry nodes modifier, and we're just going to pick up this one, which has our ETK UV lattice. I'm also going to just make sure that I also have my original mesh actually coming through here. Here we go, group input, she's back. Now I need to bring in a new UV map, because right now I don't know what the UV map is called for our plane, object. If I come into here, I've got my UV, I've got my plane selected. I'm going to go into my data, object data properties, go to the UV maps, and I can see capital UVM lowercase ap. Back to Suzanne, I'm going to plug from the group input into my UV map. Here we go. And I'm going to just tell it what that one is called. It's the default name, so this does actually have the same one. Now, because it's being used in context of our controller, it will be looking at the UV map from the controller. So just to be aware, this right now, this is how we bring in that UV map. I need to make sure that my plane is my controller object. I'm just going to press E on here and grab it like that. Smoothing level I have set to 3. That's fine. It basically computes a little bit of subdivision, helps us with our normals. I'm going to actually delete one of these attribute outputs just to make it a little bit clearer what's going on. Let's plug in our projected UV out here. Now the name we used in our shader was just UV, so let's call it that, like so. And now we can see that we actually have something lower down on Suzanne. Now what we need to do, I'm just going to turn off wireframe for now so we can keep an eye on what's going on. This is all you need for the geometry node setup. We're just bringing in the name of the UV map from our controller, picking the controller object, make sure that you've got the name in your modifier, outputting to a new attribute, which you bring into your shader with the attribute name. And now, if I just tab into edit mode, rotate 90 on the x-axis, let's just begin nice and easy here by bringing this forwards. Now, I'm going to make sure that my plane is not showing up textured in the viewport. Let's change this over to wire, and now we can see through it. That's a lot easier. And I might also just subdivide my mesh. Now what we want to do is essentially start moving our controller until it fits Suzanne. This is going to be hideous. This is essentially how you can set it up to start creating your own monstrosities. I can imagine this being quite useful for more organic stuff. And here's the thing, right? This is not a pretty layout, but let's say you have a good UV unwrap on your object, but you've just had difficulty remapping this kind of planar texture to it, and you want that kind of control. Maybe it's something more natural and you want to just push it around like this. We can now go into our object, right? If I get another texture node, delete the image texture off here and grab just the UV map off our actual Suzanne. Let's create a new one. I'm just going to do it small. I'm going to call it test. Here we go. Just a black image. All I need to do now, so I'm just going to view directly the output from this image texture. I know I've not put it in a good position, but let's just go with what we have. We're in cycles. I'm going to go down to bake. I'm going to set this over to emission, and we just need to make sure that we select our test here. It's driven by our local coordinates. And now I can just bake that new texture map. And you can see that this is now how that texture map looks according to Suzanne's actual unwrap. So I'm not going to pretend that this is like a really flexible, amazing way of working and you should all do it. but you can actually create stuff which can be exported in this way. It requires a little bit of baking, of course, because we're doing like really manual gizmos here. You know, if I move this around even just a little bit, we're going to significantly move where our mapping is. So, all good fun. You could do some fun stuff with setting like animated displacement on this, and it's going to mess up how it maps. So maybe you can get some interesting effects that way. Now, at some point, it's not here yet, but we will be able to just write this directly to our UV channel on Suzanne, in which case you'd be able to pass this out directly to your game engine or whatever you're using it for. Even just while editing this video, I ended up coming up with some new nodes and changing some other nodes. So there have been a few little tweaks and improvements along the way, a couple of bug fixes and 3 new nodes. So I'm going to show you those here and also tell you where they are in the menus. So first of all, let's have a look at the 2 wires. This is actually a new addition into the curves collection. You can find this in here. And it essentially takes any kind of geometry, whether that is a mesh, a curve, or even a point cloud, and it will turn it into hanging wires. Let me just show you that. Probably best if I show you with something like an icosphere. And so the icosphere looks something like this. And if we put it through our to wires node, you can see that it turns into this kind of drooping wires. So we can set our droop distance, and this is also a field, so we can put in a random value as well. We have a wire resolution, which you can see is going to allow us to set the pointiness of these wires, maybe for stylized or maybe for performance reasons. 12 is a decent midway place. We also have the actual profile resolution, so by default I've got these set to 3 just to be super low res, and we have the wire thickness. Essentially how that works. So it does work well with a random vector. If I just grab in a random float in here, plug this into my drop distance, we can now see that we have a whole variation of different tensions on the wires. And in fact, if we add a few of these, let's maybe duplicate our icosphere by just instancing it on a line. So let's grab a mesh line with an offset of 0. This is a nice easy way to duplicate things. Instance on points. So the line is our points, our icosphere is our instance, and then we'll just plug this in here and make sure that we are realizing those instances. You can now see that we get all sorts of different tensions, all of these laying over each other. I'm sure you can come up with some really nice effects for this. So that is the 2 wires node. Any sort of geometry you can plug in here. If you were to use something like the grid, which we can see is actually a point cloud, I set this to something fairly low, like 3, and maybe increase the randomization. So disconnected points, but this is still going to find a way to connect them up and give you that look of wires. And next up, I'm going to show you the Transform Plus. So this one is a little variation on the general transform node. It is slower because it's actually doing it inside the mesh. It's using the set position as opposed to the transform. But this allows us to do things with selections. If I add something simple like a cube, and I'm going to make it a little bit bigger, and let's turn on the wireframe so we can see what's going on here. Let's make it up to 2. And we'll go something like this. So we have quite a lot of vertices. And let me demonstrate the problem. If I add a normal transform node and I move this up quite high, maybe 5 meters, and I move it off to the side as well. And now if I want to transform this again, and maybe this time I want to rotate it. If I rotate it, I'm going to be rotating it around the world origin. And obviously when we're used to modeling in 3D, G, S, and R by default will work around the bounding box centers. So that's what I've done here, is I've turned this node from the general transform node into focused on the bounding box centers. Now if I rotate this in the y-axis, we can see that that is working around its own center. And equally the scale will go towards its own center. Now we can also set a custom center. So the world origin would be 0, 0, 0, right? And we can set whatever position we want for this. So you may have a particular position that you want to be scaling towards. Now this is also a field, so you could even have a particular point per vertex that you are positioning towards. So with that turned off, it's just going to go around your actual bounding box center instead. Now another cool thing about using the transform node, which by the way is in the utilities transform just at the bottom, transform plus. Great thing about this is it also has the selection. So now we can have a little look at our selection prism. So this is a little bit different. We have left all of our selection nodes exactly as they were in the earlier parts of this video. However, I also just added a visualizer. So there is now a preview output on all of these. And if I just join this up with a join geometry node to the preview, here we go, we can now see that we have this as a preview. Now, it's important to remember to unplug this ultimately because this is real geometry, but it essentially outlines the position where this selection is taking place. So for example, if I set this up to a little bit higher, maybe 5, and we're going to reduce the radius so it's a smaller point, something like that, and maybe I do a little bit of rotation and move it up. So the great thing about this is that I can now actually see, I can see what's going on. I don't have to guess anymore what's going on with these selections. So I have that. I can now disconnect it because, you know, I don't really want to be using this in later transforms. Let's keep it on for now just so we can see. But I'm going to make my ETK transform plus. Maybe I move these up just a little bit. We can see that just happened. Maybe I also rotate it and let's scale it slightly. So right now this is happening to everything, but we can plug in our selection region. And now you can see that it's just happening to that. And the good thing about this is the selection region is also going to govern the center of the bounding box. So it's not like an object center. It is a selection center. You can see as I rotate this, it's rotating around the center of that selection. This is just a really nice way of working. It's a little bit more intuitive. It's a little bit more like what we used to in the 3D viewport, being able to actually move stuff around and yeah, rotate around the actual selections that we make, as well as being able to see the selections. So selection prism, that one has a view. Selection sphere has one. Selection plane has one. Selection cylinder and selection box. All of the shape ones have one of these previews, so you can see. Now, while the plane and the cylinder and the prism, these should technically be infinitely long, just for the sake of being able to actually move around and not be thrown off into an infinite distance away. I made sure to just keep things within a 50-meter scale, just to make things a little bit easier there. You can see as I move these, we can have a full view of what's actually going on here with our selection. Just makes things a little bit easier to work with. All right, so that's our selection prisms as well as our transform plus node. My recommendation is if you just want to move stuff around, use the transform node because it's a little bit faster. It's around about 10 times slower, 5 to 10 times slower, the transform plus, but it also has considerably more utility. Final node we want to look at today is going to be the Raycast plus, and I'm actually going to do a little setup for this. So if on my monkey, I make a new node tree and I add from my utilities, Raycast plus, and I can just drop this on. So this is behaving exactly like a regular Raycast, but it also takes through our main geometry. It also takes that through, and it outputs a visualizer. So this is why it's taking it in, is because we also need to visualize the rays. Otherwise, it's exactly the same as a regular Raycast node. There's nothing fancy going on here. This is just about the visualization. It should help if you're maybe a little bit unsure about your Raycast, or you're doing something where you need a little bit more finessing. You can do something like this, plug in your preview, and just remember that this is a real preview. It's not an overlay, so you will need to disconnect it later. Just need to bring in our Torus object, set it to a relative, and we can plug that in and we can see all of these rays being visualized from Suzanne. So if I move Suzanne around, you can actually see what's going on. This has the ray as well as the surface normal being visualized here. So that's awesome. And we can still plug everything in, like we could manipulate the source position, or we could set a ray direction. So maybe we set the ray direction to this surface normal instead. So now Suzanne is actually shooting out in all directions from her surfaces, and we can see each of those rays where they hit our torus and the direction of the normal at that position. So it's just a really nice way for us to work. And anywhere that we do not have a hit, it just doesn't draw anything. So there we go. And this is dependent on the points. So if I was to add a subdivision surface to her just before in here, then you're going to see that we're getting more points because it's basing it entirely on the number of vertices. All right, so these are our additions today: the Raycast plus, the Transform plus, and the 2 wires, as well as the visualization within the Raycast and the selection nodes. Hopefully this has helped. Leave me any comments with ideas for new nodes, any bugs that you've found. I will fix them as soon as I can, and stay in touch. I'm always really excited to see the kinds of things that you make. Hopefully you're enjoying the nodes. I know there's a lot to get your teeth into, and there will be more to come. Thanks for watching. I'll see you around.